Okay, so in the previous lecture, we covered started chapter 8.8. We covered 8.1, 2, and 3, in which we introduced the potential energy of a system, and then spoke about conservative versus non-conservative forces and about conservation of energy. Today we'll be talking about potential energy diagrams and stability, and then we'll chat a bit about sources of energy. It should actually not be a very long lecture. It should be nice and easy. Okay, so let me get the chat screen on here as usual. Good. Okay, so let's define what is a potential energy curve, okay, and then explain how do we read it, okay. Now, we spoke about gravitational potential energy, and we derived it to be equal to mgh. We also spoke about elastic potential energy, and we defined it to be as half kx squared. And in either case, this was defined as energy due to position of object. Okay, we spoke about references, reference levels. Now, what this also means, another way to look at it, okay, is that this potential energy, which for now I will call U, okay, so U, I'll call it potential energy, and U will represent all sorts of potential energy. So whatever elastic potential, gravitational potential, other types of potential will all generally be labeled as U. Okay, actually, half mv squared is not potential energy, it is kinetic energy. So half mv squared is not potential energy, it is kinetic energy. So you have it because of movement, not because of position. Okay, so now generally speaking, in our world everything is three-dimensional, okay, or 4D if you want to include time, but let's stick to 3D at the time for the moment. Your potential energy is not only usually mgh, it depends on your position in 3D. Okay, but for the case of this course, to simplify matters, let's only consider one dimension, okay, the x dimension. So I will call it u of x. Okay, all right. Now, if I plot x and u of x, what does this plot give me? This plot gives me the amount of potential energy at any given position. Yeah. So at this position, this is my potential energy. At this position, this is my potential energy. At this position, this is my potential energy. Okay. How did we get energy? we said integral of F dot D equals energy, right? So if I now take energy and I do the reverse, so I do d by dx of energy, what do I get? Anyone? Excellent. I will go back to my initial position of having force. Okay. Now d by dx on a graph is what? D by dx on a graph is also known as gradient or slope. Okay. So if I have a graph of u of x versus x, and I find what my slope here is, I know what my force is. So to go back, okay, delta U, the change in potential energy, we defined it as minus the integral of f of x dx. Okay, we said energy equals F dot D. For cases of continuous forces, we put in an integral. Delta U is U final minus U initial okay, which can be written as minus initial to final integral f of x dx. Okay. Now, if we want to go back to f of x, I just differentiate my u. My minus sign carries on. So you get minus du by dx. Now, the very important point is, okay, that this equation 8-11 in your book, f of x equals minus du by dx, is only valid for a conservative force. Okay. Why is that? Can anyone tell me why? I'll go back to 8.11 in your book. Can anyone tell me why is it only valid for conservative force? Why it isn't valid for non-conservative forces? No loss of energy, no loss of energy because it's constant, work constant, no friction. Okay, you are all correct in one way or another. Remember, what was our definition of a conservative force? Our definition of a conservative force was that it doesn't matter what road we take, the amount of energy used or gained is exactly the same. The work is the same, independently of the path taken, right? So it makes sense if we say, let me go back here. If we say I am starting at this point and I am ending at this point, it makes sense to me, okay, or it makes mathematically sense to say that, well, I have an energy associated with this position, and I have an energy associated with this position, because how we go from this position to that position is independent of path. I can take a straight path, I can take this path, I can take this path, and I would still end up with the same work done to go throughout this time, this distance. Okay, so it is easy for me to say that U final of x is equal to U inertial of x plus work done, because work is independent of path. But what if I have a non-conservative force where each path has a different value? What would the result of that be? I would still have UF equals UI plus X, but then my work would be path dependent. So work A would not be equal to work B, would not be equal to work C. So when I want to define UF up here, based on what do I define it? It is the potential energy is no longer only dependent on position, but also on path. And we cannot define it until we know the path. Okay, so this equation only works. Sorry. So this equation only works in cases where the force is conservative, mainly because this is the only case where we can actually define energy as the function of position. Is this bit clear? Open this to see. What we do later depends on understanding this part clearly. Okay, no comments. Okay, so for one-dimensional motion, f of x equals minus du by dx. Let's take the example of the potential energy of a spring, half kx squared. Okay. What will I end up with f of x? Well, d by dx of half kx squared will get me d by dx of half kx squared will give me half 2 kx. This go away, and I get kx. I have a minus sign here, so minus kx. And this is what our force, what we know our force for gravity, for springs is. F equals minus kx. Let's try another thing. U of x equals mgx. mgh, whatever. I'm going to put it x so it's easier to use d by dx. Minus d by dx of mgx will be? Anyone? Minus mg. Yeah, remember we have a minus sign here. So we have a minus mg. Okay, which is m, and then the g is downwards. So that's why. Okay, very simple so far. Lubna conservative means that going from point A to point B, your final energy, your initial energy and final energy is position dependent. It doesn't depend on the path you take. Okay, so the definition of conservative force, as we did it in chapter 7 and chapter 8, is the work is independent of path. So usually when we calculate work, we do F dot D and integral. For conservative forces, whatever the path is okay. You will always get the same final answer, no matter how you go from part A to part B. This is why when we do problems with potential energy and something is raised from this height to this height, We don't care if it's going in a straight line, if it's going like this, if it's going like this, if it's going like this. We will always calculate potential energy to gravitational potential energy to be equal to mgh. Okay, we will not consider what path has it taken to get to that position. Let's see if we have understood this. The figure below gives the potential energy function u of x for a system in which a particle is in one-dimensional motion. Rank regions AB, BC, and CD according to the magnitude of the force on the particle, greatest first, so from biggest to smallest. Okay, one student said B. One student said C. One said B. So most are saying B. Some C's, some B's. Couple of D's. Okay. We define force as minus du by dx, which means minus gradient. Which one has the biggest gradient? CD has biggest. Big. Which one has the second biggest? BC has a gradient equals to 0. Okay, because it's a straight line, so its gradient is 0. AB also has a gradient. Okay, here the gradient is less than 0. Now, because it said according to the magnitude of the force, not the force itself, according to magnitude, the biggest number is CD, then AB, then BC, which is 0. So this one, C. Okay. If we said if we did not say magnitude, if we said according to the force, okay, then again it would have been the same. CD, AB, BC. If we said in terms of positive force, only then would it be AB, CD, BC. Okay.
دكتور دي نفس الإجابة تعتقد؟
Oh, yes. CD, AB, BC. Interesting. I made a mistake here. Sorry. Yes, so this is the same thing. CD, AB, BC. Well, no. Area would be integrating. We are differentiating. Okay, area, you would be integrating the energy. So you would be finding what is your total energy, or what is your work, rather than what is your force. Okay. Now, this is a very quick revision of stuff that we did already. Okay, but I'd like to just go over them very, very quickly. We said that if we wrote the mechanical energy as the sum of potential and kinetic energies, we get our total mechanical energy. If we just rearrange this, we see how kinetic energy varies with potential energy. We simply subtract the potential from the total, and whatever is left is kinetic energy. Now, here's a pendulum. And there is something interesting about it. These two points that are written as TP, turning point, okay, there is something that always happens at them. As soon as the ball reaches TP, it stops and reverses direction and goes back down again. Every single time without failure. So this TP is actually an important point. Okay, it's a special point that we're going to give it a name. Okay. At equilibrium points, okay, we call it an equilibrium point where things are equal. Our kinetic energy is 0. Our velocity is 0 because it stops, but our force is not 0. Our force is maximum because it starts going back down again. If the force was 0, it would not be going back down again. Okay. All right. So let's take a plot of potential energy, U of x versus x. Now there are some certain interesting points here, okay? This point and this point are special. Why? If I put a small ball here, what would happen if I move it a little bit? Zero force, it would stop. H equals 0. Okay. Don't think about force and physics things now. Just think of it like a game. If I have something that looks like this, like a U, and I put something and I put the ball a little bit. Yes, here we go. Someone thought of it as a game. It would go back to where it came from, right? As soon as I move it slightly up, it will just come back down. It would want to come back down to this point, right? This point is nice. There is something special about it. If I try to, if a ball is here and I try to move it a little bit, it will want to come back. It will slide back down. Okay, what about if I put a ball here and I put it very, very carefully? Okay, here. I put it very carefully so that it doesn't move and it is stuck at that point. What is special about this position? Okay, so if I have a ball here, or if I have a ball here, okay, since my force is minus du by dx and the slope here is all 0, my force here will be equal to 0, my force here will be equal to 0, my force here will be equal to 0. Okay, but there's a slight difference between the three of them. In position 1 and position 2, this is a nice slope equals 0. Okay, the slope equals 0 here and the force equals 0. And if I try to take the ball out of it, it will come back to the trough. It will come back to this point down here. On the other hand, at point 3, slope is 0, force is 0. So all three, 1, 2, 3, are equilibrium points. Okay. But So all three of these are equilibrium points, but in points 1 and 2, this equilibrium is nice. The ball wants to come back. But in point number 3, although it's an equilibrium, it's a bit different. If I just push the ball a tiny bit, what's going to happen? Think of it as a game, as a ball game that you have. Forget physics for a second. It's going to move, and it's going to fall down. It's going to move away from this point. Yeah. So although the ball is stable there is no force, no potential, the slope is 0, it's not moving. The tiny thing, it's not going to go back to it, like in points 1 and 2, it's going to go away from it. Now this has a name, okay? The red is a plot of the potential energy. The blue is a plot of the force. So we take the slope at every single point in red and we do the force. Now you will see something. At x1, okay, actually, I'm not going to draw it because I already have it here. Reminder, F is minus du by dx. At this point, force is 0 and potential is 6. It's straight line, there is no force. The slope is 0. At x equals 1, where the potential is falling down, okay, a little bit after x equals 1 here, if I take minus du by dx, I will get a very strong force because I have a very strong gradient. What about x2? x2, I have a stable point, 0 slope, so I will get 0 force. Let's keep doing this. At this point, I will again have a force. It's not as strong as this one because the slope is a little bit less, but it's still there and it's in the opposite direction. Okay. Okay. So we keep doing this and we see a clear correlation, okay, between the magnitude of force and between the slope of the potential. Now, here we have a force, here we can have a force, and here we can have a force as well. The forces which take the ball back to where it was, okay, so these positions, these two positions, we call stable equilibrium. F is equal to 0. And if F is more than 0, then it is a stable force. Okay, sorry, not stable force. My bad. Restoring force. Where have we heard this term before? Restoring force. Have we heard it somewhere before? Spring, excellent. Spring, okay? This is why springs always want to go back to their 0 point. This is a restoring force, okay? On the other hand, this point up here, okay, is what we call a non-stable equilibrium. F is also equal to 0 here, but if F is little bit more than 0, then what I call the snowball effect. You see in movies where we have this tiny snowball which moves at the beginning of the mountain, and as it rolls down the mountain it becomes bigger and bigger and bigger. This is what happens here. If you give it a tiny, tiny force, it's going to get bigger and bigger and bigger and bigger and fall down. Okay. Now, what else can we learn from one of these plots? These plots are actually really, really useful. Okay. Now, maybe not in the sense of physics 1, but generally they're very, very useful. Let me give you an example. If we know that the total energy is 5 joules, my total mechanical energy, this gives me a maximum potential energy, a maximum kinetic energy, a maximum velocity. Okay. Now my kinetic energy is my total energy minus my potential energy, which is the difference between these two lines. Okay. Now if I look at x equals at x5, my kinetic energy there is simply total energy 5 minus potential energy 4, so 1 joule. Okay, and then I can use this 1 joule to do half mv squared and find what my velocity is. What about here? What is my kinetic energy going to be here at this point? It's going to be 5 minus 1, which is 4. What about here? 2, 5, no potential energy here, full kinetic. Here my kinetic energy is 0, all my energy is in potential energy, and I kind of have a tiny, tiny problem, because if I try to find my kinetic energy here, I will get minus 1 joule. And I cannot have minus 1 joule, because if I have a kinetic energy of minus 1 joule, it means my V is negative, which is an imaginary number. So I kind of have a problem. There seems to be a really big problem with this plot, because it wants me to have negative velocities. Not negative velocities, sorry, negative square of velocities. So this is a problem. We'll come back to this. Okay. So, turning points, kinetic is equal to 0, but force is not equal to 0. This is what we call a turning point. Okay, so this is an example. My kinetic energy is equal to 0. My velocity is 0, but my force is actually the slope here, this way. I still haven't solved my problem here with my minus 1 joule. How can I have a negative kinetic energy? Now, see, there's no problem with having a velocity which is more than 0, less than 0, yeah? So if my velocity is minus 10 meters per second, that is not a problem. I'm going 10 meters per second in the reverse direction. But then my V squared is still equal to 100, yes? Minus 10 squared is still 100, still a positive number. Now, since my kinetic energy is half mv squared, and I have a v squared here, it needs to always be positive. Or my square is negative, which is a problem, or my mass is negative, which is an even bigger problem. Okay. And I'll still come back to this. I'll solve this problem at the very end. Now, what if my total mechanical energy is equal to 4 instead? Well, I will have my potential energy, my turning points at these 2 points, where my kinetic energy is 0. 2 different things. Here my kinetic energy is 0, but my force is not equal to 0. But here my kinetic energy is 0, and my force is equal to 0. And these are 2 different things. Okay. This is a turning point. This is an equilibrium point. Okay. But again, equilibrium points are not all the same. I'll summarize all of this in a bit if you're confused. Okay. الفيل هذا ورانا كل مكان من بداية الكورس. صبروا لما الفيلة تبدأ تدعم سيارات الليكتشر الجاي. زين. Now there's a very big difference The area under the curve represents simply the total energy while you're moving from point A to point B. Okay, now I have here two photos of equilibrium points. Okay, but these two equilibrium points are very, very different. Okay, there is this elephant who is in equilibrium, but the tiniest push will make him go fall down. On the other hand, you have this ball here, which is in rather stable equilibrium. Yeah, it's not at danger of falling at any given time. Let's reduce the total mechanical energy even more to 3 joules. My turning points, and now I have 2 turning points and 1 equilibrium point. And now I have an unstable equilibrium, which we said before, it will be very happy to fall down to a lower state of energy. Let me skip all of these, and then I will give you a summary of all of this. But to summarize, in a U of x versus x graph, we can see the following. We can see turning points, Ke equals 0, force is not equal to 0. We can see equilibrium points where force is equal to 0, but we have 2 options here. We have stable and unstable. Stable means push equals restore. Unstable means push equals snowball. Okay, what do they look like? This point is a turning point. This point is a stable equilibrium. This point is a non-stable equilibrium. EP is equilibrium point, yes. E is equilibrium, meaning equal. Okay, now how do we explain this mathematically? Sorry, F is equal to 0, not equal. Okay. How do we explain this mathematically? Mathematically, we say, if we have U of x, if du by dx is equal to 0, equilibrium point, and then if I take the second derivative, can be more than 0 or less than 0. It can also be equal to 0, but we're not going to go into that now. If it is more than 0, then we have a maxima. It's less than 0, then we have a minima. Okay. This is 8.4. Do you remember this from school? How to find the maximum of a function and a minimum of a function? Take the first derivative, make it equal to 0. Take the second derivative, then you have maximum or minimum. Yeah. Well, it turns out if you have a function of a force or a function of a potential, you don't need to do all the drawing that we did now. You can simply do the derivatives and find where is it a maximum, where is it a minimum. Okay. Let's do a PIQ. The figure below gives the potential energy for a system in which a particle is in one-dimensional motion. The particle is in the region AB. What is the force on the particle? Positive, negative, or just simply zero? A, B, C. We have a spread of A's and B's. No one believes it's zero, but most believe it's A. The correct answer is A. Slope here is negative. Force equals minus slope. Minus minus is equal to plus. So the force here is positive. Okay, we have already done this before. We've already done these before. I'm going to skip them. Okay. Okay. So far, yes, we can get it by the graph also. You're correct. Now, so far, whenever we spoke about external forces acting on a system, we said they were doing some kind of work. Okay, and we did F dot D. But it actually is possible, this is a side note, okay, for forces to act on a system without doing work. Okay, how so? Consider, any of you have ever done ice skating? Consider an ice skater. You're holding the rail and you push yourself away from the rail. Okay, what's happening is the skater is turning her internal chemical energy into kinetic energy. The change in kinetic energy here is caused by the force from the wall. But the energy does not actually come from the wall because the wall cannot give her energy. Right? By conservation of energy, okay, my work, my change in energy must come from somewhere. Okay? Now, I know that my total mechanical energy, okay, increases because my kinetic energy increases. Initially, I was not moving. My KE was 0. Now I'm moving, so my KE is more than 0. So where did that energy come from? Okay. The answer is the wall couldn't give me the kinetic energy because the wall did not lose any energy. It actually came from inside me. It's an internal energy, chemical energy from my muscles, from the food I eat. It's still given by the same formulae, just that we need to be careful what the source of our energy is. Is it internal? Is it external? Is it the thing that is making us move? Is it not? Which leads us to section 8.5, which is sources of energy. Now, this is more of a chatty section. Okay. Now, when we studied energy, we learned that it can take different forms. It can transfer from one form to another. Okay. But until this last slide, we never spoke about, okay, where is this energy come from? We always assumed there was some energy. Okay. Now, the question is, where do these energies come from? Okay. So I'll give you some examples and I'll tell you some stuff. Okay. It's interesting where we get our energies from. Okay. There isn't really much to be examined in this section, but it's an interesting information. So, for example, atoms and molecules inside all objects always jiggle. There's always a random motion. They have internal kinetic energy because of this, and we call them thermal energy. Okay, because it is related to the temperature of the object. What else? What other kinds of energy do we know? We know like electrical energy. It's where we use all of our electricity. We have fuels, gasoline, petrol, diesel, food. All of these have chemical in it. Okay, this is potential energy because of the molecular structure. They're bound to each other. They have potential energy. And what happens is once your body starts, for example, digesting food, it breaks down the bonds, the chains between these molecules, okay? And it releases that energy and gives your body energy to sustain itself, okay? So someone wrote, Noor, yes, ATP, adenosine triphosphate, you're absolutely correct. So adenosine triphosphate is key into the process of breaking down energy and breaking down molecules and taking the energy out. You're absolutely correct. Okay. Light has a lot of energy in it. Okay. Light is one kind of electromagnetic radiation. We have radio, infrared, ultraviolet, X-rays, gamma rays, cosmic rays, so many different types. Okay. And anything with thermal energy actually radiates electromagnetic waves. Now, some of them, like our light bulbs, emit it in the position in the spectrum which we can see from, but some don't. Some emit in other frequencies which we don't see, like X-rays. For example, light is both a wave and a particle. Okay, it is a bit of both. It's neither a particle nor a wave, but it's both a particle and a wave. Okay, it is what we call the duality of matter. Okay. Sometimes it's easier to think of light as waves. It makes calculations easier. Sometimes it's easier to make to think of light as a particle. It makes other calculations easier. Okay, I'll actually show you something interesting at the end of this lecture about light, if you're interested. Nuclear energy. Okay, if you have heavy atoms with 238, 240, 250 protons and neutrons all stuck together, they have bucket loads of energy, and they have so much energy and they're cramped in such a tight space, they're not really comfortable being all together in that same space. So all you need to do is just bring a neutron in the right thing. Now remember, these things are very, very tiny, so it's difficult to do this. But all you need to do is get a neutron, go ting, and this tiny extra energy that goes ting, okay, gives enough of these protons and neutrons inside, enough energy to go, hey, I've got loads of energy, I don't need to be here anymore, I'm not bound. And they leave the atom, and that big atom fizzles into two smaller atoms, okay, and releasing energy in the process. This is how all nuclear energy works, okay? The one we really know about is uranium, but you can also do things with other heavy molecules. One example that comes to my mind at the very quick now is thorium, plutonium also. Hydraulic energy or hydroelectric energy, maybe you mean? The one from water, hydroelectric? Yeah, you're absolutely correct. Okay, we have hydroelectric energy. And hydroelectric energy is actually very, very interesting because it comes from a different class of energies. Okay, you might be reading a lot about these, hearing about a lot about these in the news. Renewable versus non-renewable energies. Okay, now non-renewable energies are by definition, once you use them up, that's it, they're finished. Okay, now some people might ask, okay, where did they come from? Why do they finish so quickly? Okay, surely just like it was manufactured, like it was made in the first place, they are still being made in deep down in earth. But here is the problem. Okay, now in Oman and the Middle East, the most famous example is oil, petrol. Yeah. Now here's the problem. Yes, they are constantly being made, but imagine this: all the oils that we have been using since we discovered oil, maybe, I don't know, 100 years, 80 years ago, okay, it took it tens of millions of years to make this amount, and we might finish them in like 100 or 200 years. Yes, if we wait another another couple million years, we will have more oil again. But the problem is, what happens in those years between those millions of years when we finish up all the non-renewable? Okay, this is called non-renewable. We cannot renew them. We cannot, once depleted, okay, once you use them up, they all go into heat. Yeah, if you burn petrol or if you burn gas, you get a lot of heat. But then that heat you cannot, remember when we spoke about conservative and non-conservative forces? By definition, heat is not a conservative force. I cannot take this heat and then make it back into oil. Once it's gone, it's gone. This introduces a new class of energy sources, which we call renewables, and in which we try to harness nature in its natural form without screwing it up. Okay, so things like, for example, solar. Yeah, now we get sunlight all the time. Okay, we're in Oman, we know, for God's sake, we have way too much sunlight and it's too hot. We can capture this heat, we can capture this light, okay, and we can do it in many different ways. Okay, you have solar thermal, you have solar concentrated power, you have a solar photovoltaic, where you are capturing light and converting it into electricity, and this doesn't finish. Okay, this doesn't finish because, well, it comes from the sun and comes every single day. Okay, maybe in a few 100 million years, our sun is going to die and implode and explode and we're going to end. But then you don't really worry about not having enough sunlight because you're more worried about not dying. Okay, you have geothermal heat. Okay, you have geothermal heat. Places like New Zealand, for example, are putting long rods inside volcanoes and getting that heat. You have hydropower. Someone mentioned hydropower, Lubna. Okay, you put dams. Okay, you have ethanol, biodiesel, wind power, ocean power, and there's a very, very important question. Okay, why nothing has been done about it? If we have so many natural sources for natural energy, why have we not done anything about it? Okay, and the question is, it is not always as easy as it sounds. There are always downsides and upsides of every single one. I will tell you very quickly, since this is a chatty session, yeah, I'll tell you very quickly some of the pros and cons of each one of these, which makes it sound, which makes us know why or why not are we doing or not doing it. Okay, one problem, as Dubna said, is it's expensive. Okay, until the last few years, okay, it was much more expensive to get a solar panel in place than to simply burn oil. Okay, and this is a big problem. Okay, because, well, humans by nature, we are greedy and we don't like to spend money. Okay, so if I can buy petrol and burn it for much cheaper, I'll just do that. Someone else will, figure out the whole renewable. Once it's cheap enough, I'll use it. But then when enough people say this, we are stuck because no one is actually doing anything about it. Okay. Also, it takes a lot of space. You have different problems. For example, in Oman, we have a lot of sand and غبار واجد. Okay, and this is a very big problem because once the dust comes on the panels, you need to clean it up. Okay, you also need to fix it. Someone said تصليحه غالي. You are correct. Yeah, it is expensive to fix it, and you need infrastructure. You also need to, for example, solar power gives you DC current, not AC current. So to inject it into the electrical grid, you need to make it, to change it into you need to convert it to AC. This is extra cost. But here's the interesting thing, and this is very important, especially for you as the new generation. This is very important. You might be hearing more and more and more. Okay, I'll stop sharing the screen. Okay, you might be hearing more and more and more about how we have a problem with oil prices, and how the oil prices have dropped, and how it's a very big problem because, well, now Oman cannot have the government, we cannot have enough money to sustain ourselves. Okay, الميزانية فيها عجز, etc., etc. Okay, and one of the things that's happening is, well, COVID and all of that is happening. But what is actually happening, and it has been ongoing for a long time, unfortunately, in the Middle East, many times you don't realize what's happening to us until it's too late. Okay. Within the last 10 years, okay, the prices for solar power have dropped, and for renewables have dropped considerably. Let me show you something. Okay. Okay. So let me show you something. Present window. Can you see this? What did I just do? Can you see this? The cost per watt for silicon solar cells was $76, which was ridiculously expensive, considering, the cost for petrol at the time was something like, 0 point something or 1 point something. So no one's crazy enough to go. But recently, during the last 10 years, due to continuous advances in technology, okay, we are down to 0.3 or even less. 0.3 was in 2015. This was 5-6 years ago. Okay, it's going down and down every single year. So it's becoming cheaper and cheaper to do things like solar power. And actually, a lot of countries, for example, in Europe, I don't know which is الموقع. I just went to Google and wrote down price of solar power per kilowatt. Okay, now there are problems. So, for example, امتنان says يحتاج اهتمام وتنظيف دائم. But there are ways to go about it. This is the whole thing about technology. Yeah, we shouldn't wait for other countries to make it. We have a problem with dust. We need to fix this problem. We need to find a way how to do it, rather than wait for some other country or some other company to make it, and then we buy it from them as a ready-made system. Okay, and actually during the last 10 years, countries, for example, like Germany, have increased their solar power generation into the grid by 10-fold or 15-folds. Okay, and this is one of the reasons. Okay, this is one of the reasons why oil prices are going down and down and down, and we're having more and more difficulty in Oman or in the Middle East to get more money for our oil. As countries and companies move towards more and more towards renewables, we will have more and more problem in selling our oil. Okay, or selling our oil for good enough money. Okay, so we need to also start moving to a different economy. And this is why we have Vision 2040. Okay, Vision 2040, out of which now Vision 2024 has come as a sub-project. Okay, this is one of the main goals, to diversify our economy. Okay, you have, for example, solar hot water. Very easy, very nice, but you need very pure water for it. Okay, you have, for example, hydropower. Now, hydropower is a very nice source of electricity. The problem is you need to build really, really big dams, and the areas behind the dams get flooded. Okay, if you're interested, read up on the Three Gorges Dam, Gorges. This is one of the biggest dams in the world. It was made in China, and it literally floods entire cities, entire communities, entire populations need to be uprooted and told to go live somewhere else. Okay, because this whole area is going to become a water reservoir. Okay. Also, the cost of changing technologies. Okay, so cars at the moment work on petrol. Now, to make them work on something else takes a lot of investment and a lot of new technology. Not everyone wants to do that. Wind power. Wind power is one source. Well, in Oman, it's useless. We don't have a lot of wind. Okay, but even in countries which have a lot of wind, okay, you have an issue. They look ugly and they are huge. Okay, so there are downsides and upsides to each one of them, and we need to have a balance, okay, of all of these sources of power to be able to sustain life on the long term. Now, one last thing I want to say before we end this lecture. We have spoken quite a bit about conservation of energy, okay, and maybe in the media or when you're reading articles or books or watching videos, you might hear a lot about energy conservation. And these two things, although they sound the same, are not actually the same. Okay, so conservation of energy is what we call the law of conservation of energy. Energy cannot be created or destroyed. It can only be switched from one form to another. Okay, it's very useful to analyze physical processes in physics, in engineering. It cannot be proven from basic principles, but it's very, very good bookkeeping device. And so far, this has been going on for at least a couple hundred years. Okay, we have not found a single exception. On the other hand, philosophy of energy conservation is the idea that humans need to live within their means. Okay, we need to live within our means. We need to reduce usage of resources. This is what energy conservation is. It has nothing to do with conservation of energy as in physics, okay, but energy conservation. And what that is, for example, it's winter, don't have the AC on. It's summer. When you leave home, don't leave the AC on. Don't leave the lights on. Okay, reduce your carbon footprint. Okay, if you and your friends or you and your family members are all living beside each other, take one car instead of taking 3-4 cars to go to the same place. Okay, this is the philosophy of energy conservation. Okay, with that, we end chapter 8. And inshallah, on Wednesday, we start with chapter 9. Okay. Stop recording.